Hi there. In this video, I'll be doing the first half of the odd practice for section 2.1. And I'll just remind you, I'll be going through this rather fast, talking somewhat quickly. Please pause and rewatch things as necessary. So for number 1, we have position versus time, right? And always pay attention to what we're actually measuring instead of just assuming. So the horizontal, the input is time. The vertical, the output is distance. And so A is estimate the instantaneous velocity of the elevator at t equals 10 seconds. So velocity is a rate. Rates are like slopes. Instantaneous slope is like slope of the tangent. And what we'll notice here is that here the tangent line is really following the graph. This graph seems to be perfectly linear, at least for a little while. So to figure out the slope of that thing, well, we notice here's a nice easy point. So we'd notice like, oh, the change in, let me do a different color. The change in time appears to be 5 between those points. Right. Don't just follow the grid, actually look at the values. And the change in position, I'll just call that P, appears to be 20 meters. So that slope is 4. It doesn't look like a slope of 4 because of the units. But for A, we're basically looking at 4 meters per second. And if you're ever not 100% sure about your units, think it's y per x, right? Slope is y, change in y over change in x. What's playing the role of y is the position measured in meters. What's playing the role in x is time measured in seconds, so 4 meters per second. B is asking you to sketch a velocity versus time curve for the motion of the elevator. What we'll notice is that basically we have yikes, I opened a different file. What we're noticing is we essentially have 2.5 seconds here where the time is moving, but the distance is not. The elevator is not moving. And about 2.5 seconds at the end where the same thing is happening. In between, we're following a line, and the slope of that line appears to be 4. So essentially what's happening is velocity is 0 for a little while. Then it abruptly switches to 4. Then it abruptly switches back to 0. So a graph here. So this is time in seconds. But we're talking about velocity in meters per second. And what seems to be happening is for about the first 2.5 seconds, it's 0. Then it switches up to 4, and then it looks like around 17.5, it switches back. So essentially, our graph looks something like so. Velocity is 0 for a while, then velocity is 4 for a while, then velocity is 0 for a while. And it's sort of a question of interpretation. Maybe it makes a really abrupt change and an abrupt change like that. Or maybe it literally just switches, right? So if you did it like this, where just out of nowhere there's a jump, that's plausible for this graph. It's a little bit hard to tell, right? Is it a sharp corner here, or is it just a really quick transition? We don't know for sure. That's not the point of this problem. But what is the point is to realize that from position we understand velocity, and we can answer it as a question like what's happening at one specific time. But we can also think of it globally. What is the whole story about velocity? If we know everything about position, we actually also know everything about velocity. Next one is problem number 3, which also has a picture, but I didn't copy the instructions. So this is just position of a particle along a line. Right? That's kind of our standard boring motion example, just a particle. So find the average velocity over the interval from 0 to 3. So average velocity is an average rate of change. But we'll notice from 0 to 3, right? Let's just call this f. Distance is measured as f. What we're doing here is f of 3 minus f of 0 over 3 minus 0. But f of 3 and f of 0 are both 10. This is 0 over 3, which is 0. The idea is this particle wound up where it started. that means its average velocity is 0. It had positive velocity going up, negative velocity going back. But on average, it didn't move. Right? That's a little bit weird. You think this thing is moving. But on average, if it winds up where it started, the average of all of that is not moving. Where is the instantaneous velocity 0? So instantaneous velocity is a rate. Rates are like slope. So when is the slope 0? That appears to be happening right around here. The slope of the tangent, if we zoom in, there's a place where the graph is actually very horizontal. And there also appears to be one right around here. So one of them appears to be happening around t equals 2. One of them is pretty close to t equals 4. If you zoom in, you might argue it's more like t equals 4.1. And then I guess you could also argue at t equals 8. Those are the places where the graph appears to be doing something horizontal. The slope is 0. Slopes are rates. So the rate of change, the velocity, the instantaneous velocity is also 0. C is asking when we think the instantaneous velocity is at a maximum or minimum. So maximum velocity would mean moving forward as fast as possible. That seems to be here, right? And again, velocities are slopes. Velocity is a kind of rate is a kind of slope. When I say I want velocity to be as big as possible, we're thinking, where is slope as big as possible? And I would argue right around here is where we have the biggest upward slope. So maximum velocity occurs around t equals 1. Minimum velocity would be when the slope is as low as possible, which means big negative. The biggest negative slope, biggest negative steepness, happens right around here, around t equals 3. So you want to get super duper comfortable with these translations. It's a question about velocity, which is a kind of rate, but you're answering it based upon slopes. And then finally, D, find the instantaneous velocity when t equals 3. Well, velocity is a rate, rates are slopes. So what we can do is, as best as we can, just by drawing it in by hand, draw a line that you think captures the steepness of this graph at that point. Right? I'll do my best. So I'll draw it really small and then extend it. Right? And we're just doing our best guess. We're estimating. All of these we're asking us to estimate. So something like so. And I'll just do my best to figure out coordinates. So this one right here, I know is at 3, 10. Let me do that in a color that shows up better. 3, 10 is that point. This point right around here, x coordinate looks like it's about 2.3. Y coordinate is 15. So that slope, the velocity there is the same as the slope. So y minus y over x minus x, negative 5 over 0.7. So that is negative, and I don't have my calculator with me, I left my office, but that's to 3 decimal places, I think it's that. And, oh, I'm sorry, I forgot to move my decimal. I believe that's correct to 3 decimal places. This is what's important. You could just leave it like that. And the units here would be centimeters per second. So the big theme here is rates are slopes, slopes are rates. Answering a question about one might require thinking about the other. Okay, number 9 asks us to sketch a line that is tangent to a curve at 2 different points. And I'm going to cheat. The easiest way to do it actually is draw the line first. And here we go. So here's my curve. It's tangent right around here. And then maybe later on, it's tangent again. So we can have something where the same line perfectly captures the direction of the graph in one place and then perfectly captures it somewhere else. That will happen from time to time. Okay, that was number 9. And we're going to do 11 and 13, which are both multiparts. So 11a and b, 13a and b. So here I'm not writing out the instructions, presumably you have it. So for number 11, we're given y equals 2x squared, x sub 0 equals 0, x sub 1 equals 1. For part A, we're asked to find the average rate of change. Let's call this f. It's easier to talk about things when we have a function. So our average rate of change is f of 1 minus f of 0 over 1 minus 0. If I plug that in, I get 2. B, did I ask for A and B? Yes. B says find the instantaneous rate of change of y with respect to x at an unspecified value x0. So we're no longer worried about this particular value of x0. We're now thinking unspecified. So instantaneous rate of change, same as slope of the tangent, right? Same calculation. Our function is f of x equals 2x squared. And we're just thinking there's this general x sub 0, unspecified. So how do we figure that out? The slope of the tangent, or I'll say IROC. We think that it's the limit of an instantaneous rate of change. So x sub 0 is the specific number we're thinking about. Up top, we would think change in f. So f of x minus f of x0. In the bottom, we're thinking change of x values. And we're taking the limit of this as x approaches x sub 0. Right, the trick here is we don't have a specific number. It's more powerful if we don't have a specific number. It's like we're basically doing all the problems at the same time. So this would be the limit as x approaches x sub 0 of 2x squared minus 2x naught squared over x minus x naught. This is a factor and cancel thing. Factor out the 2, and then it's a difference of squares. So it factors like so. So we'll notice that this cancels, and we have the limit as x approaches x naught of 2 times x plus x naught. And now we plug in. And what's a little awkward is we're plugging in x is, well, not some specific number that we've been told, but this unspecified number x naught. So when we plug in, x is now x naught, and this simplifies to 4 times x naught. But what we've actually done is infinitely many problems at the same time. If this is the function and I asked you what's the instantaneous rate of change at x naught equals 5, well, you've already done it in general. So it's 4 times x naught, which is now 4 times 5, which is 20. If I ask you for this function, what's the instantaneous rate of change when x naught equals negative 1? Well, you've already done the work. It's 4 times negative 1, which is negative 4. And then we're going to do the same thing for number 13. So for number 13, the function is 1 over x, and in the original example, it's 2 and 3. So for A, we're just doing an average rate of change. So f of 3 minus f of 2 over 3 minus 2, 1/3 minus 1/2 over 3 minus 2 equals negative 1/6 over 1, which is negative 1/6. For B, it asks us again to do this instantaneous rate of change in a general way, for an unspecified x sub 0. So the general pattern, right, at some level you just kind of want to memorize that this is what you can write down. Looks like this. Our specific function here is the reciprocal function, 1 over. So this more specifically would look like 1 over x minus 1 over x naught over x minus x naught. And now we just algebra our way through this. So our common denominator is x times x naught. So after we combine the two fractions in the numerator, we have x naught minus x all over x times x naught. we'll notice that these are opposites, so they cancel, yielding a -1. And, oh, that's a times, yikes, can't. So we've canceled away the 0 over 0 issue, and now we can plug in. Wherever we see an x, we'll write x naught. And so this is -1 over x naught squared. And again, what's powerful here is what we've done infinitely many problems at once. If I ask you for this function, 1 over x, what's the instantaneous rate of change when x equals 3? You don't have to redo anything. You can just apply this formula. If x naught is equal to 3, I have -1/9. So moving forward, we're usually going to do these kinds of calculations for some unspecified value. So then we have just a pattern that we can apply over and over again rather than do the same calculation every time. But obviously the function matters. This rule only works if we have the function 1 over x. All right, I'm going to stop this and I'll do the other part in a different